Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Electrostriction from the paper Functional Materials. After this lecture, we will be familiar with the following. First, electrostriction. Second, the mechanism of electrostriction in piezoelectric materials. Third, electrostriction coefficient and its dependence on various factors. Fourth, determination of electrostriction coefficient. Fifth, the advantages and the application of electrostriction. So students, let us start with a basic introduction about this module. Electrostriction is the property of all electrical non-conductors, for example, crystalline, amorphous, solid or liquid, or dielectrics that causes them to change their shape under the application of electric field. It is a non-linear property of a material and forms the basis of all electromechanical coupling in insulators. It has wide range of applications as far as ferroelectric materials are concerned. Unlike the piezoelectric effect, the electrostriction describes the phenomena in which the strain varies proportional to the square of the electric field or the polarization. So now students, let us discuss how this electrostrictive effect occurs. When an electric field is applied, the electrostrictive strain response can be written as Xij is equal to Qijkl PkPl is equal to Mijkl EkEl, or we can write it like that: X is equal to Qp square equal to Me square, where P is the electric field polarization and Q is the charge related electrostrictive coefficient, which is nothing but a fourth rank tensor. That is why it is represented by Qijkl. E is the electric field and M is the field related electrostrictive coefficient, which is also a fourth rank tensor. Q, being an intrinsic property, is a constant for a material and is independent of the temperature. So for a linear dielectric P, it is directly proportional to E. Hence, the relation between the M and the Q can be easily found out. Now, in non-conducting, or we can say in the dielectrics which are non-linear in nature, as a consequence of the permittivity which relates P and E becomes dependent on the strength of the electric field, thus making the value of M dependent on the same. That is, as it is shown in this figure, that the dipoles formed due to the electronegativity difference, on applying the electric field, the dipoles, they have been increased due to the application of the electric field. That is, in non-conducting materials which is lacking the positive and the negative ions, the difference in the electronegativity of the constituent atoms result in the development of dipoles which interacts with the applied electric field. So, for the isotropic polymer with an electric field E in the third principal direction and a polarization response P in the respective directions, the polarization P in the respective directions is given by x11 is equal to q1133 p square is equal to m1133 e square, or we can say that x1 is equal to q13 p square equal to m13 e square, or similarly the x3 is equal to q33 p square, or it is equal to m33 e square, where x3 is the strain produced in the direction of P and x1 is the strain produced in the direction perpendicular to the direction of P. So, we can say that electrostrictive strain is a function which is involving the even power of the applied electric field. In electrostriction, the sign of deformation that takes place with the applied electric field is independent of the polarity of the field. This indicates the fact that in electrostriction, the expansion is produced in the direction of the field regardless of its polarity and reverts back to zero when the field is removed. Mechanism of electrostriction. Electrostriction is the measure of the polarization which is caused by the displacement of ions from their original equilibrium positions on the application of electric field, ultimately resulting in the variation of lattice parameters or the development of strain. Electrostriction is caused by small displacement caused in the position of ions from its original position on the application of electric field. Positive ions are displaced along the direction of the applied field, whereas the negative ions they are shifted in the opposite direction. This displacement affects the material in bulk, resulting in the overall strain in the direction of the field. The strains produced in the orthogonal directions are characterized with the help of Poisson's ratio. The insulating materials lacking ions but having different kinds of atoms shows the property of electrostriction owing to the electronegativity difference in the constituent atoms, which induces dipoles within the system. Some more facts on the mechanism of electrostriction. In the case of ferroelectric materials, electrostriction is believed to take place due to the field activated coalescence of micropolar regions to macrodomains of the parent ferroelectric. Consequently, the mechanism is essentially the same as the nonpolar cubic prototype of the ferroelectric phase undergoing a momentary phase transformation to the ferroelectric phase while under the influence of an electric field. So for relaxer, ferroelectrics have the two mechanism, and these
proposed mechanisms are, according to the first mechanism, the interaction between the soft lattice polarization and lattice distortions with the charge transfer fluctuations and with the active ion displacements is the reason for electrostriction. For the localized NBO-NB and ONBO triads in the disordered relaxer state. The second mechanism is based on the effect of simultaneous interaction of quasi-local vibrations with the soft lattice polarization and lattice distortions.
So now let us discuss how can we determine the value of electrostrictive coefficient. Five approaches have been proposed for the determination of electrostrictive coefficients. These are based on number 1, strain polarization versus electric field curves, dielectric permittivity versus stress curves, piezoelectric effect for the ferroelectrics, the lattice parameters, the dielectric permittivity under DC biased electric field. So now let us start with the coefficient determination with the help of strain versus polarization or electric field curve. In this method, the electrostrictive coefficient is measured by analyzing the strain versus polarization electric field curves. The equation, which is given as, that is the xij, which we have already studied, is equal to qp square equal to me square, forms the basis for such kind of measurement. This method is applicable for determining the electrostrictive coefficient of materials having a high dielectric response where the strains can be measured with minimum errors. So, this is about the method. Now, the advantages are it is the most common method used that includes the detail of the strain field information, which is easily and readily available. But the basic issues which are behind this method is that the domain switching can affect the value of electrostrictive coefficients to a very large extent. Now next is the preferable materials which are used for this method are the materials with high dielectric constant and the materials which are having the high elastic compliance constant, they are generally preferable. Now the basic examples or the materials whose coefficient has been determined by using this method are the perovskite ferroelectric polymers. So the next method for coefficient determination is with the help of dielectric permittivity versus the stress curves. In this method, we use the converse electrostriction to establish a relationship between the dielectric permittivity and the applied stress. From the direct effect of electrostriction, Qijkl can be expressed as Qijkl is equal to half of del square Sij divided by del Pk del Pl. So with the help of Gibbs free energy and changing the order of differentiation, we get the converse effect of electrostriction as given by dgl, or we can say dg1 is equal to minus Sij dxij plus ei dpi minus s dt, where G1 is the elastic Gibbs free energy, Xij is the stress, S is entropy, and T is the temperature. And here chi KL represents the inverse dielectric permittivity. So this was about the method. Now it has certain advantages, that is, it is a good supplement to the first method, which is generally used to determine the hydrostatic electrostrictive coefficient, that is QH. And the issues over here are the occurrence of non-linear phenomenon such as depolarization and phase transition on the application of stress is the main cause of error in the measured Q value. And the preferred materials which are used or whose coefficient has been determined are the materials with low dielectric coefficient, with the low dielectric constant, and low elastic compliance. The examples are fluoride perovskites like calcium fluoride.
So students, let us discuss how the electrostriction coefficient can be determined with the help of piezoelectric effect on ferroelectrics. So the method which is involved over here is that the coefficient is measured by studying the variation in the piezoelectric coefficient of the ferroelectrics under concern at different temperatures. The advantages of this method are: this method can be used to determine full Q matrix of a ferroelectric material. And the issues from this method are the piezoelectricity developed in the material under the study should originate only through electrostriction. The preferred materials for this method are the ferroelectric single crystal with the parent phase of centrosymmetry, and the examples are lead titanate, barium titanate, PMNPT, lithium niobate, and various other single crystals.
Next method is the coefficient determination with the help of lattice parameters. Now in this method utilizes the basic parameters of the lattice to determine the strain in different materials, and using the value of the strain and polarization, it determines the electrostrictive coefficient. This method states that the Q coefficient can be obtained as the ratio between the spontaneous strain and spontaneous polarization, that is Qijkl equal to Sij divided by Pi square, where Qijkl is the electrostrictive coefficient, Sij is spontaneous strain, Pi is the spontaneous polarization. Now here the basic advantage of this method is does not require the presence of high electric field or stress. But the basic or the main issue with this method is that it can be used only for ferroelectric materials. For example, lead titanate, barium titanate, and lead zirconium titanate, that is PZT. So the last method to determine the coefficient is by studying the dielectric permittivity under the DC biased field. Now in this method, the coefficient is measured by studying the variation in the lattice dielectric permittivity under a DC biased field. Now here, this method is developed by Patnaik and Taulos, and they derived an expression for the dielectric permittivity involving the electrostrictive coefficient M with the cubic symmetry. So, in this method, the real and the imaginary parts of the dielectric permittivities have been expressed, and in terms of the static and the infinite frequency limits of permittivities, the omega, which is the angular frequency, the tau, which is the relaxation time, the elastic constant, and the DC biased field. Now the advantage for this method is that the electrostrictive coefficient can easily determined with the help of dielectric permittivity, and this method also establishes the relationship between the dielectric permittivity and the Q, which can be used to enhance other properties of a material. And the basic issue or the main issue for this method is that for the determination of coefficient, using this method, the dielectrics must obey the Debye model.
Effect of microscopic properties on the electrostriction. The microscopic properties such as ionic radius, ionic charge, and the crystal structure affects the extent of electrostriction effect in the solids. In simplest rigid model, the effect of microscopic properties can be written as Q11 is equal to 12 G R naught to the power 5 divided by F Q square, where Q is the charge of the ions per ratio represents the comparison between the anharmonic and harmonic energy components, and R naught is the distance between the cation and the nearest neighbor of equilibrium position. The effect of microscopic properties is symbolized by G, R naught, F, and Q. For perovskite materials, it was observed that the electrostrictive coefficient strongly dependent upon the level of the order-disorder of B-site cation arrangements. Experiments they were carried out to study this effect, and it was finally concluded that electrostrictive coefficient, that is Q, increased with the order level of the B-site cations from disordered to partially ordered and then to the ordered structures. In order to explain this phenomenon, the K. Yukino proposed a schematic crystallographic model. So according to this model, a large rattling space was expected to be occupied by smaller B cations for the ordered structures. On the contrary, the smaller rattling space was expected to be occupied by B-side cations in the ordered arrangements, where neighboring oxygen atoms were densely packed around the smaller B ions. When the electric field was applied in the disordered perovskite structure, the cations in the large rattling space could easily shift without distorting the octahedron framework, resulting in a larger polarization and lower strains for unit magnitude of electric field. So this results in smaller electrostrictive coefficient, and students, they note over here that they have large dielectric permittivities. So when an electric field was applied to the ordered perovskites, the smaller rattling space for B-site ions prevented the motion, resulting in the development of strain and further distorting the octahedron. Thus, it was observed that the ordered B-site cations resulted in enhanced electrostrictive property. This model is one of the simplest models explaining the effect of microscopic properties on electrostriction. So, for accurate measurement of electrostrictive coefficient from the microscopic characteristic curve, some other complicated methods have also been proposed.
The effect of macroscopic properties on electrostriction. While considering the macroscopic properties, we take into account the two important properties. First is the dielectric and elastic responses, and second is the thermal expansion. Using a simple atomistic model, Newnham proposed a relationship between the dielectric, elastic, and the electrostrictive effect. As an electric field is applied, the cations and the anions in a crystal structure, they are displaced in the opposite direction by delta R. This displacement is responsible for the electric polarization, dielectric permittivity, and the electrostrictive strain. And the electrostrictive coefficient to this first approximation is written as Q is equal to x by p square. It is approximately equal to delta R by delta R the square, equal to 1 by delta R, approximately equal to 1 by epsilon, where epsilon is the dielectric permittivity, x is the strain, and p is the polarization. For a certain electric field, a larger delta R corresponds to a larger epsilon. The electrostrictive coefficients were also closely associated with the elastic compliance S. So now the converse effect, the electrostriction is proportional to the change in the inverse dielectric permittivity chi with the stress. That is, Q is equal to delta chi by x equal to x by x by s is equal to s. So where Q is the electrostrictive coefficient, delta chi is the variation of chi on the stress x, and small x is the strain on the stress x. So combining these two equations, the electrostrictive coefficient is proportional to S by E. Now the next property is the thermal expansion. The electrostriction and thermal expansion originates from similar mechanisms, that is potential and harmonicity. As such, the thermal expansion and electrostrictive coefficients are thought to be interrelated. Based on the similar manner in reducing the electrostrictive coefficients, the thermal expansion can be written as alpha is equal to 3g kb divided by 4f square r naught, where kb is the Boltzmann's constant and r naught is the distance between a cation and its nearest neighbor anion at equilibrium. F and G are the harmonic and the anharmonic components respectively. Similar to electrostriction, the thermal expansion coefficient was zero when the anharmonic effect was ignored.
Now let us discuss the advantages of electrostrictive materials. Electrostriction can also be used to improve the piezoelectric property of a material. In fact, it has numerous advantages over piezoelectricity. These include: first, hysteresis in strain field dependence is minimal or negligible in a selected temperature range. Second, deformation in materials is more stable and comparable to piezoelectric ceramics. Third, no poling is required.
Now let us discuss the applications of electrostriction. First, the application which we are going to study is the electrostrictive actuators, and see this figure which shows the miniaturized ink worm and the oil pressure servo valves where the electrostrictive actuators are being used. The electrostrictive actuators, they are also used in the capacitive stress gauge, whose figure has been shown, in the ultrasonic motors, and also in the deformable mirror or the wavefront correctors.
Electrostriction also finds its application in: first, field tunable piezoelectric transducer, micro angle adjusting devices, flex tensional transducers, bistable optical devices, interferometric dilatometers, vibration suppression elements, actuators with an hysteretic tunable nature, and lastly, in the improvement of piezoelectric constant.
The criteria for the selection of ceramics for electrostrictive devices. So this table gives the criteria for selecting the ceramic for electrostrictive devices. The desirable properties for the selection of ceramics are: first, large strain, induced polarization and piezoelectricity; second, large operating temperature range; third, low loss, low joule heating, minimal hysteresis, no remnant polarization. And the material behavior properties for the selection are: large dielectric constant, broad dielectric transition, operation in the para-electric regime, that is T greater than Tmax.
So, students, Let us summarize what we have learnt in this module. First, electrostriction is the measure of the polarization which is caused by the displacement of ions from their original equilibrium positions on the application of electric field, ultimately resulting in the variation of lattice parameters or the development of strain. Second, the measure or the various approaches to find the electrostriction, that is, strain polarization, electric field curves, dielectric permittivity, stress curves, piezoelectric effect for thermoelectrics, the lattice parameters, the dielectric permittivity under a DC biased electric field have been discussed. Third, the effect of microscopic and macroscopic properties of a material on the electrostrictive effect are discussed in detail. Fourth, various applications of electrostrictive materials, including the electrostrictive actuators, capacitive stress gauge, ultrasonic motors, and deformable mirror wavefront corrector. Lastly, the criteria for the selection of the material for electrostrictive devices are discussed. Thank you.